Hey, how's it going, guys? So for this problem, I'm gonna take a different approach. I'm gonna go ahead and start, because these problems are getting very long. I'm just gonna go ahead and do the problems and just kind of uncover my paper as I go. So this problem is no different than the previous one. Just find the displacement vector, right? Your slopes and your displacements, and then you find your force vectors, which is your force, moments, all that good stuff, and obviously that's the reactions, right? And then the forces in each element, and then at the end we're going to draw the shear and bending moment diagram. So let's go ahead and get started. All right, so nothing crazy, right? Same thing, just like the other problems. We start off with our stiffness matrix, and we're going to apply this stiffness matrix to every single element. Let me get a pencil real quick, just so I can point at things. In this case, the only difference between these two beams, right? You have two 5-footers, but I mean, they have the same material, E and I, right? But this one has, you really can't see it, but it's 2 times the moment of inertia. So this one's twice as, I mean, I can't even describe that moment of inertia thing, but you know how you do EI over L cubed for both beams? In this case, this one is going to have twice the magnitude of this one because I is up top, right? So just real quick, before you get into all that stiffness of each element, you start off with the boundary conditions. So the boundary conditions, things, you have 2 degrees of freedom at each node, right? Displacement in the y, and then rotation at each node. In this case, we go ahead and just start applying it, right? V1, it's fixed, node 1, so that means V1 and Phi1 are both 0, okay? V2, if you apply a force here, it's going to come down some distance, and you're going to have some deflection, right? So we don't know V2 or Phi2. And then V3 and Phi3, same thing, right? If you apply a force here, and even if you didn't have this force, right, this thing is still going to move because of a force. So just because we know this doesn't necessarily mean we didn't know this and that. I hope that makes sense. It's kind of like, ignore this 5 kilopounds for now. If you had this one, you still wouldn't know these two, okay? Or ignore this one. I mean, this would also displace, right? Just think of it logically. If you apply force here, these two are displacing, and they're going to have some angle of rotation. But just FYI, you got to kind of see this stuff once you start doing these problems on your own. So in this case, we don't know the 4 degrees of freedoms in these two nodes, right? We only know these two, V1 and Phi1. So if you know these, that means you don't know the force or the moment. And if you don't know V2 or Phi2 or V3, Phi3, that means you do know the force and the moment. Okay, so just something to keep in mind. So once that's done, you go ahead and just start assembling the global equation, right? The element stiffnesses before, I'm sorry. Let's go there. So because this one has twice the moment of inertia, it's better to separate it out so you kind of see it. This is what happened, look. Initially, we're using this stiffness for each element, right? But because one is twice as big as the other, in this case, element 1 is twice as stiffer than this one, the magnitude for element number 1 is going to be 2 times, if that makes sense. Okay, so just give me a second. This is what I'm trying to tell you guys. When you do EI over L cubed, originally L is 5, which is 60 inches, right? I is 200 inches to the 4th, and then the modulus is 10 times 10 to the 6 psi. So your units are pounds and inches. When you do EI over L cubed, you're going to get 9260, okay? Now, since this one has twice the EI, you're going to get 18520, I think that is, okay? So for element 1, you were supposed to get 18520 on this side, but I only put 9260. Instead, what I did was, since this was 2 times EI over L cubed, instead of multiplying this by 2, I multiplied everything inside by 2. So look, this was 12 4L squared, 12 4L squared that got converted to 24 8L squared, 24 8L squared. And everything in that matrix also got converted, okay? Now you do that, the reason you want to do that is because this value here, you want to have it the same as this one. So that way when you make your global stiffness equation, right, your global stiffness matrix, you'll be able to just add all these elements together. And 9260 is your common denominator. Think of it that way, okay? So in this case, I did that, right? Instead of putting 18520 here, I put 9260, but I just multiplied everything by 2. All this is just this matrix up here, right? Between nodes 1, V1, Phi1, V2, Phi2. So element 1, the beam itself, is between nodes 1 and 2. So V1, Phi1, V2, Phi2, V1, Phi1, V2, Phi2. Then for K2, same thing, right? 9260, that one, that's just the true value of the stiffness. It's V2, Phi2, V3, Phi3 because it's between nodes 2 and 3, okay? So once you have all, and again, we know L, by the way, that's just length, 60 inches. So all these values we know. We know this number, so that means we know K for every element. So once you have that, you're able to add them, okay? The only ones that are going to overlap are V2 and Phi2 because both elements share the same node, which is node 2, okay? So these 4 are going to get added to these 4 right here. That's exactly what we did right here. We assembled the global equation, right? So it's just forces equal to Kx. So F1y, M1, F2y, M2, F3y, M3 is equal to 9260 times your global stiffness, right, matrix. So if you look at V1, Phi1, V2, Phi2, and then V1, Phi1, V2, Phi2, these elements, these numbers right here, are just this matrix. Okay, I just threw them in there. And then these V2, Phi2, V3, Phi3 are right in here. Okay. Now the only ones that overlapped were these 4. So this 24 got added to this 12, right? The V2, 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 V2 is this number 24. Then V2, V2 got added, that's 12. So that's 36. Same thing, negative 12L, 6L will give you a negative 6L. Then negative 12L, 6L will give you a negative 6L. And then 8L squared, 4L squared will give you a 12L squared. And everything else stay the same, right? All these columns are just these right here. So here's where it gets a little crazier, right? Now, I already did it, right? So it's kind of hard to follow, but these were V1, Phi1, V2, Phi2, V3, Phi3. In this case, we already knew V1 and Phi1, right? So we just plugged them in. Now, you remember I said when you know one, you don't know the other. And when you know this one, so I guess what I'm saying is you always know at least one of them. You never know both. You never not know one, okay? So in this case, since we know the displacement, we won't know the force. And if you know the force, you won't know the displacement. So before you got to this, it's good to see this. Know your boundary conditions, right? We had 2 of them out of 6, 0 and 0. So that means we don't know F1y and M1. Because we didn't know these 4, we should know these right here, okay? Now, just by looking at the actual diagram, you're able to verify that. So you got 5,000 pounds pushing down. So that's a negative 5,000 at node 2. There's 0 moment, right? There's no clockwise or counterclockwise arrow. So that's 0. And then at node 3, you know negative 5,000, right? You see it going down, and you see it right there. 0 moment, it's applied. There's nothing going on at node 3, so that's 0. So just like that, you got these 2, and then these 4. Now you could solve it, right? You have, in this case, 6 equations, 6 unknowns. 1, 2, 3, 4, 5, 6 equations. And then your unknowns are F1y, M1, V2, Phi2, V3, Phi3. Now, before you do that, right, you want to focus on, you want to start crossing them out. In this case, we know they're zeros. So when these two, V1 and Phi1 are 0, we cross out V1, Phi1, V1, Phi1 in the x direction, right? Left to right. So that means we're left with this matrix right here, a 4x4. And we're going to solve for V2, Phi2, V3, Phi3. So that's what we did here, right? Let me just hide the answers for a second. Right there. So this is what we did, right? I just put negative 5,000, I divided 9260, and that's how I got negative 0.534. So when you do that, right, let's start with the first one, with F2y. It's negative 0.534 equals, when this, okay, you know what, let me start over one more time. It's negative 5,000 equals 9260, but 9260, I moved it to this side, so that's how I got negative 0.534. And then follow it, right? 36 times V2 minus 6L times phi2. It's going to look like this, look. 36 times V2 minus 6L times phi2 minus 12 times V3 plus 6L times phi3. And that's exactly what I did here, right? 36 V2 minus 6L phi2 minus 12 V3, 6L phi3. You set that equal to the negative 5,000 over 9260. Do the same for the other ones, right? 0 is equal to, in this case, divided by 0 goes away. So you have negative 6L V2, 12L squared phi2 minus 6L V2, 2L squared phi3. And that's the second equation right there. And you continue it, right, for the other two. And you get these 4 equations, 4 unknowns. Now, what I did was I went ahead and plugged it into this website that you're seeing right here. And I was able to get it right. At the end of the day, it's just the systems of equations. If you could do it by hand, if you have a graphing calculator, that's going to save you on the exam. If not, it's better. I mean, it is what it is, right? You got to know how to solve them. And you can solve them, right? It just takes longer. But hopefully your professor will let you. So these are the values right here. Now that I have V2, phi2, V3, and phi3, now I can solve for the other two. Okay, so what I'm going to do now is I'm going to assemble F1y is equal to 9260, right? And this is what I'm doing right here. So F1y is equal to 9260. 24V1, but V1 and phi1 are 0. So let's go straight to this one. It's going to be minus 24V2 plus 12L phi2 plus 0 phi3 plus 0 phi3. So in this case, it's just these two numbers. I already went ahead and computed them. I did negative 24 times V2, which was that number. And that's the number I got. And I did the same thing, right, for the next one, 12L times phi2. Phi2, we got it right here. That's the number. And I was able to solve for F1y. Same thing with M1, right, is equal to 9260 minus 12L phi2, V2 plus 4L squared phi2. Okay, that's all that is. So I was able to find those two. And the next step after this is just verifying it. So an easy way to verify it is through statics, right? So let's go ahead and I'm going to show you the answer right here. Do a quick statics check. Very easy. Sum of the forces in the y direction. Whatever goes down is equal to whatever's going up. So in this case, you have 2 5,000s going down. So that means going up should be 10,000. F1y, I calculated to 9890, but that's just rounding error. That's 10,000 pounds. The moment at 1, well, you just take a moment about 0.1. So it's just 5,000 making a moment, and then another 5,000 making a moment. So it's 5,000 times 5 feet or 60 inches. 5 times 60, that is some number. Just do the math, right? Minus 5,000 times 60, it's a negative moment. So you're going to put negative. Minus 5,000 times 120 inches. And whatever that value is, that should equal your moment that you got here. And in this case, it's 900,000 pounds times inch. 900 pound inches, my bad. And that's how you solve for that's how you verify that the answers that you got up to here are correct. So if these numbers make sense, that means for sure these numbers are correct, or else they wouldn't make sense if that makes sense. So now the next step is to get the forces in each element. This is easy to do. At this point, you just start using the same stiffness values that you were getting for this side right here. My bad. Got the flashlight with my other hand. But you use this K matrix to solve for the forces in each element. Okay, you don't use, in this case, no, I'm sorry, that doesn't apply for this problem. You always use the K, okay? In all of my problems, I put a K matrix up here, and it's just the basic 12 4L squared, 12 4L squared. That's the one you use when you start solving this stuff. In this case, check it out. This is how I set it up. For element 1 was between nodes 1 and 2, right? So it's V1, Phi1, V2, Phi2, right? 24 8L squared, 24 8L squared. Now, it's 24 8L squared. It would have been 12 4L squared, but remember, this would have been 18 520. But I just went again and threw it on there. Now, once you do that, right, this is V1 Phi1, V2 Phi2, same thing. V1 Phi1, V2 Phi2. We calculated these, so we're able to just throw them in there, and we're able to find our mini F1Ys, M1, F2Y, M2. Okay, so once you do that, it's just same thing we've been doing, right? F1Y is equal to 9260 times 24 V1, which is 0, right? V1 and Phi1 are 0, so these two get crossed out. So now you're just here. In this case, negative 24 times this number, 0.3115 negative, is going to give you 7.476. And then 12L times this negative number, 0.0089. Because at the end of the day, you're just doing matrices, right? Matrix algebra. F1Y is equal to 9260, 24 V1, 12L Phi1 minus 24 V2 plus 12L Phi2. That's what I did here. I did that F1Y, was able to find F1Y. Then M1, same thing, right? M1 is equal to 9260. 12L Phi1, which is 0, 8L squared Phi1, which is 0. I might have said Phi1, I meant V1. Minus 12L V2, which is some number, right? Times this number. Plus 4L squared times this number. That's what I did here. And did the same thing for the other two, right? And I got my forces in each element number 1. In this case, F1Y was equal to this number, but rounding error is 10,000 pounds. M1 is equal to 890,000, but it's 900,000 pounds, inches. F2Y was negative 10,000 pounds. M2 is negative 300,000 pound inch. Now, we'll verify these numbers, not yet though. You got to do this for every single element, and then you can verify it. So in this case, yeah, let's just keep it going for now. You'll see what I mean. So come down. I did the same thing, right? For element number 2 is between nodes 2 and 3, so that means V2, Phi2, V3, Phi3, right? And then same thing, 12 4L squared, 12 4L squared is the stiffness of that element. Then you're able to solve for your F2Ys and all that good stuff right there. So F2Y is equal to 9260, 12 V2, 6L Phi2, minus 12 V3, 6L V3, right? And it's just 12 times, this is V2, and 6L times Phi2, minus 12 times V3, 6L times V3. That's what I did for the first one. I already converted the numbers, and I was able to solve for F2Y. Do the same thing for M2, right? We'll do another one. Let's do M3 now. We did M2 up here. We did M1 up here, so let's do just another random one. M3 is equal to 9260. 6L times V2, 2L squared times Phi2 minus 6L times V3 plus 4L squared times Phi3. And that's that. And once you solve for those numbers, you'll get that right there. F2Y is about 5,000 pounds. M2 is equal to 300,000 pound inches. F3Y is equal to minus 5,000 pounds. And M3 is equal to 0. Okay, so let's verify them. This is the last element, right? In this case, we only have 2 elements. So let's verify it. When you verify this, you have to make sure that your little F1Ys, F2Ys, F3Ys, M3s, M2, M1s, when you add them all up, they have to give you the big values, okay? So I'm going to show you just the last part right here, but hold on. So what I'm trying to say is when you add all the little ones on the back side of this page, you're supposed to get your big F1Y, which is 10,000 pounds, M1, which is 900,000, M2, which is negative 5,000, 0, negative 5,000, 0, okay? So let's go ahead and do F1Y first. It's positive 10,000, okay? So let's go ahead and double check that. get all your F1Ys and add it together. In this case, look, we have one F1Y right here, none, 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 and then none here, boom, just one of them. That should be 10,000 pounds. So cool, we verified that one. Let's verify the next one, right? Moment one, we calculated 900,000 pound inch, okay? So that means your M1s should equal 900,000. In this case, we only have one M1, right? Nothing here, nothing here, nothing here. So M1 is 900,000 pound inch. So cool, that's verified. Let's verify another one. F2 is negative 5,000. And then so is F3, and so is moment 2, moment 3, okay? So F2s should give you negative 5,000. So let's go ahead and check. F2Y, and then you have another F2Y. This is negative 10,000 plus 5,000 will give you negative 5,000. So that's good, it's verified. F3Y should be negative 5,000. Let's double check it. None here, boom, this one, negative 5,000. M3 was 0. Now you get a number, I think, or maybe you don't, I can't remember. But it's so small compared to 900,000. I mean, it's pretty much 0. So M2 should be 0, remember? So M2 here is 300,000 pounds, but this M2 is negative 300,000. So boom, add them up together, you get 0. That's how you verify it. Now let's go to the shear and bending. Now let me explain this in a second, but this is just static. So if you're good at shear and bending, you should be all right. It's just statics at the end of the day. So this is our beam in question, right? You have 5,000 pounds going down at node 2, at node 3, 10,000 going up at node 1, 0 moment, and then you have a moment reaction, right? 900,000. So let's draw the shear. You start from this side and you work this way. In this case, you get bumped up 10,000. Nothing happens, nothing happens, nothing happens. 5,000 brings you down. Nothing happens, nothing happens, nothing happens. Another 5,000 brings you down. And that's exactly what you see here. So the first F1 pushed us up 10,000. Nothing happened along the beam until node 2. Brings you down 5,000. Nothing happened until node 3. Brings you down another 5,000. So that's the shear diagram. That one's simple. Now to get the bending is real easy. You just need to know like basic integrals, right? So this is a line, right? So imagine this is a line, well in this case, right, y is equal to 10,000x. No, I'm sorry, y is just equal to 10,000. So take the integral, what's that? Well, 10,000x, right? For every inch that you move, you're adding another 10,000. That's how shear works, that's shear flow, okay? As shear moves through the beam, your bending is increasing. But I mean, it depends on the actual beam setup, but just something to know, just FYI. But in this case, what I like to do, look, is this, just get the area. 10,000 is your height, rectangle, right? And 60 is your base. So multiply these two, right? Base times height is 600,000. And because you're above the 0, it's a positive, okay? Same thing with this one. Now it's 5,000, your height, 60 is your base. So 300,000, and that's a positive, okay? So that's what I like to do. To know where you start on the moment diagram, you need to know all your magnitudes, like for moments. In this case, we only have one. Moment 1, okay? 900,000. Now, here's the thing. Moments, when they're positive, they're counterclockwise. When you're doing the shear and bending, when you're doing the bending diagram, a counterclockwise moment brings you down on the graph. Okay, it doesn't bring you up. I know counterclockwise is usually positive, so you're going to think, oh, let's push it up then. No, that's not how it works. In this case, you come down 900,000. So this is in kilopound inches, right? Moment diagram. We start at 900,000 because that's our moment 1. That's where we're at, okay? So let's check this out. Because we're positive, right? This is going to have a positive slope. So when you take the integral of a line, let me use this paper real quick. When you take the integral of a line, if this is your line, your integral could have been either this or this, right? Because imagine you have y is equal to 5. Well, that's just a line, right? but it could have been y is equal to -5. Does that make sense? So if it was y equals -5, you would have had this one when you took the integral. Because we have a positive, this is our slope. So this one, not important. So in this case, we go up 600,000, okay? So between 0 and 60, we go up 600,000. So 0 to 60, right, halfway through the beam, that's what this dashed line is, node 2, we drop down. Well, I mean, we were at -900, but we went up 600. So now we're at -300, okay? So -300, this was a slope, right? It was a positive slope, so we're going up. Remember, we're going up because of this line right here. And then once you get to that part of the beam, that 300,000 is also going to push you up, but at a slower rate, okay? So now we're going like this, if that makes sense, okay? It's still going up, just it's not as steep, okay? It's more flattened out. And yeah, you end up at 0. And that is how you do the bending moment diagrams and the shear. You know, if you're an engineer, they're gonna, if you're ever working as a structural engineer, this is important because knowing this, now you know what your demand is for moment, for shear. They're gonna tell you, hey, you know, we have this setup here that we have 2 beams that one has twice the moment of inertia as the other one. At this point, they already chose a material, right? That's aluminum right there, 10 times 10 to the 6. They already chose a cross section because you know I, so that means you know the cross section of the beam. Doesn't necessarily mean it's an I beam. It could be a circular beam. It could be a T-shaped beam, a Z-shape. It could be a stiffener, right? Who knows, right? But what I'm saying is the reason you'd probably want to calculate this to begin with, the shear and bending, is once you know what your bending is, you're able to find the MC over I, right? Sigma is equal to MC over I, and you're able to check that allowable. So you calculate margins of safety. It's like, in this case, okay, my max bending moment's -900,000. I have to make sure that my material can withstand that much load. And it could be cyclic load, right? It could just be static load, whatever the case is. But the reason you do these problems is to make sure that your cross-section can withstand this much shear, 10,000 in this case, and this much bending moment, -900,000. So that's pretty much it, right? That's the problem itself. Sorry guys, it got dark here, so I had to start using the light. Hopefully it didn't cause any issues, but if you have any questions, let me know. I think I explained everything. If not, I mean, I'll keep a lookout on the comments. Thanks.